All right, let's get started. This is, I feel overwhelmed because there's an immense number of screens here and I have to watch them all. And then I have to watch you lot and...
Oh, booklets, yeah.
Okay, there are booklets here. Is there anybody here who hasn't got a booklet yet? Anybody that side? Everyone got one? Okay, thank you.
Yeah.
Right, this it only covers the first 4 or 5 weeks, and then there's going to be another. So you don't have to carry heavy books with you. There were. Anybody else? No one? Yeah, and the second thing is if you have one train that leaves at 6 o'clock or something like that because of the strike today on the railway, feel free to leave early as you need. All right. And we'll need this for today. Okay, somebody comes late. Good. Next thing, these exercises. Is there anybody here who wasn't here last week and didn't get those exercises? Not like I've lost those exercises, but you weren't here and you didn't get Okay, who's read any answers to question 1? Question 1 is about 2 examples from practice in the handout. One of them is about placing a mirror next to elevators or lifts. It's an American textbook. Which solves the problem. Okay, I'll recap what the question is about. There was an example where people complained about lifts being too slow coming to wherever they wanted to go, and they tried to optimize the way the lifts worked, which didn't help. But then they put a mirror next to the lift, so people stopped complaining. Right? They started looking at themselves in the mirror, and suddenly the waiting time for the lifts, even though they didn't change, people didn't mind. Right? The second example was where a lot of flights were getting delayed at the British airport because people were stuck at security and didn't get to the gate in time. So an American advisor, or what's it called, consultant, an American consultant told the airport to put a sign there saying that people whose flight is within the next 30 minutes or something should jump the queue. Okay, it didn't work because it was a British airport and the British, they just don't jump queues apparently. So that was the second example. Thing.
There's a freedom fight. A lot of books pass the other day, and the books pass like a student content to as a student project.
Okay.
Sorry. I'm going to get one in a minute.
It's just for your. Okay, and then there was a third example about how a mathematically good solution doesn't help because people don't accept it. So. Any comments, anyone? No. Anyone have any comment about it? Well, fair enough. No. Anything? Okay. Second question, think about examples where operational research, now you know what it is, could help improve things. Areas, problems, whatever comes to your mind.
Train timetables.
Train timetables, yes, it could. Anything else?
Network switching. What is that?
You mean computer networks?
Yeah.
Yes, that's a good example as well. Many aspects like routing packets over the internet, designing a good network. You have to find somewhere to sit. People who come later, that's a conclusion which I'm not putting there. Anybody else, anything? Oh, because everyone's asleep. Ah. How about this one? Scheduling nurses in a hospital, their shifts, rotas. Is that something that operational research could help improve? How about planning bin collection? Okay, give me another one. Think. You're here to think. You're not here to sit and be amused by
Would you have been planning the routes for like where buses have to go and stuff?
Oh yes, absolutely. Bus routes and timetables as well. Good.
Ticket pricing for planes.
Oh yes. How do you know? Good man. Ticket prices. Airlines, but also hotel rooms. It's a similar principle. You've got a limited stock of something, and you want to sell cheap in the beginning for people who plan ahead, and then you make it expensive for the people who have to be there or have to fly. Business travelers who don't care about the price because somebody else is paying. Okay, good example. Anything else? And many other examples as well. Okay. Third question was this graph. Does it show your graph? Yes. And you were asked, okay, so the question asks for which of these roads, so this is a network, road network or a street network in a town, and which of these roads, which of these connections should you clear of snow so that you could get from anywhere to anywhere else, but the length of the streets that was cleared of snow, that's possible, is as small as possible. Okay. So who has got a solution? Only one person? How is that possible? A couple of people. It must be more. They're just too shy to put their hands up. So what's the total length that you have in your solution that you have to clear?
23.
23? Did you also get 23? Did anybody get less than 23?
22.
22? You sure? Right, so you will, in Philip's lectures, you will learn how this is done. So this wasn't perhaps fair, but it was fair in the sense that you had to think about something. And what you don't want in your solution is roads to be cleared that form where you can walk around. That's called a cycle. You don't want that, because if you remove one of them, then you can still get from anywhere to anywhere else. Okay? So this shouldn't appear in your solution. And barring that, you can just start from the shortest streets or roads on the map and keep adding the shortest one without creating this. And once you can get from anywhere to everywhere else, you get the solution. So in this case, I'm just telling you, I'm not telling you why it works. Philip is going to tell you why it works. But I'm just telling you what works. So you can start with all the ones and put them in, the shortest ones, I think. And you start with the ones. Any more ones that I've forgotten? No. Then you can do the twos. With the twos, you have to be careful. So you can do this two, and for example, this one, and these two, and this, and this, and perhaps this one. Okay, this two, can you see this one, from D to E? You don't want to add the D to E, because D to E, that would create this triangle, and the triangle is a cycle, and you don't want that. Okay, and you also don't want all of these 3 2's in your solution. You don't even want 2 of them because that would create a cycle. Any 2 you add creates a cycle, but you want 1 of them. And it doesn't really matter which one. You're just increasing the length by 2. And now, I believe, you can get from anywhere to everywhere else. Is that correct? Or is anybody isolated? So now this is called a connected subgraph or subnetwork, and actually it's called a spanning tree for some reason that you will learn about in Philip's lectures later. And that's one possible solution. There are other options, as you can see. If I started adding other 2's, I would have ended up with a different solution, so that's not the only one. And the total length is, has anybody got the count? Some 22. So there are 7 ones. 8. That's 23. I'm getting 23. So unless I'm wrong, which does happen every now and then the minimum length is 23, and this is one possible solution, but as I said, you could take a different set of the 2's and you'd still get 23, and you'd still get a connected network. And this is a solution. Okay, any questions about this? Okay, now it's time to mark your exercises. So, if you've read the book that I told you to read, you have a mark. If you know an example of an operational research problem, you get a 2nd mark. And if you've got 23 or 22, and a solution like this, you get a 3rd mark. So you will have 0, 1, 2, or 3, depending on how much you've done. And I will send the register. So into the box, it's a little box called homework. You put 0, 1, 2, or 3, and you find as usual. Thank you. And then at the end, so this doesn't count towards your mark for the unit, but it counts towards the prize at the end of the term. Okay, so let's move on now. The plan for today is to have a look at a way of solving OR problems, which is using spreadsheet software. Okay, spreadsheets. Who knows what a spreadsheet is? Most people do know, I think. A spreadsheet is a table of numbers and things like that, where you can do some computations. So Spreadsheets were actually started quite long ago. This is somewhere in ancient Egypt, well, in today's Egypt or someplace like that. But it's ancient, and we think that this was some sort of accounting for how many soldiers were, budgeting for soldiers and how much money is owed by the rich people to the even richer people, something like this. And they just kept it carved in stone like this. So that was one of the first spreadsheets, arguably. But then the important thing happened when spreadsheets came onto computers. So the first computers used spreadsheets that looked like this. So now this resembles very much the spreadsheets that we know today. This is, I think, Lotus 123, it was called. And that was sometime in the 1980s. Computers didn't have graphical interfaces. There was just letters written on the screen, and it looked a bit like this. So this is some history. Now, of course, everybody knows Microsoft Excel. Hopefully, after last week's labs, if you didn't know. So that's the kind of software that we'll be using to solve simple OR problems. And the reason we're learning this is because people do it in the industry. So when you go out there into the world and want a job, well, that's got something to do with maths, then probably you will need to use spreadsheet software. Everybody expects people to know how to do it and use it in a smart way, not just in a dumb way. And that's what we will be working on for the next 2 weeks or 3 weeks or so. Looking at a variety of simple problems and learning how to solve them. But there will be some maths hidden in them as well as the spreadsheet. Okay. So the first example problem is this problem. Now, you probably can't, well, you know, maybe you can't read the numbers, but you got the handout, hopefully, and the numbers are there. And moreover, the numbers don't really matter for what the problem is about. We can solve it in generality, and then just plug in the numbers, and then we'll know what to do. Okay? So the problem is you have delivery vehicles, white vans, okay? And to buy a new one costs £35,000. And then, what do these numbers in the table mean? The mean is, the top row is the number of years that you keep the vehicle for. Okay? And the second row tells you how much money you can get for it when you sell it second hand to somebody else. So that's the money you can get by selling it on the second hand market. And the third row tells you the cost of running that vehicle in that particular year. So during its first year, it costs £6,000 to the maintenance and servicing and so on. Okay? And petrol. And in the second year, it costs 7,000 and then 8,000. So on, it goes up because as the vehicle gets older, it's less reliable and you have to service it more often. More things go wrong, and you can imagine that. So don't question how realistic these numbers are. Realistic. This probably includes some petrol consumption increasing as well because the engine is worn and so on. And the task is to find the best age at which you should sell the vehicle that you bought new and get a new one. The question clear? Ah. Good. So how does one go about solving a problem like this? what's the first step that we talked about last week when you get an OR problem that you always have to do? Create the model. That is the first-ish step. Yes. Before you start creating the model, you actually have to understand the problem exactly, okay, and have the data. So the data are in the table, that's no problem, but we should define the problem and understand fully the problem. So what is the problem? You said that the question was clear, but if I go back here, what do I mean by the best age? Any ideas? How do you know that the age is the best age for replacing the vehicle? What is the criterion for finding the best one? Saves you the most money. Yes, that is a reasonable criterion. What did you want to say?
The point at which the running cost is just below the trading.
Point at which the running cost is just below the trading cost. Not sure. Why would that be? Yeah, that sounds reasonable, but we'll see whether it's what we're looking for or not in a bit. Okay, saves you the most money. So usually we formulate it as that the objective is to minimize the cost. Aha, so that moved us a little bit forward. But what cost? Aha. So what we're trying to minimize will be, it's called the total cost. And by the word total here, what we mean is that it's the running costs and to this we add something that's called the depreciation. Have you heard that word before? Yes, no? Yeah? Okay, so what did you hear about depreciation? Yes. Yes, so this is the, so you're both right. It's so the depreciation, the cost is the cost which you incur through your assets losing value. Okay? So the loss in value of the things you own, that's called depreciation. I won't use this so generously. So depreciation is the loss of value of assets. Okay, so yeah, it can be linear or it can be calculated using a formula and so on. That is true. But in this case, to confuse you a bit, it's actually not given by a formula, but it's given by the numbers in the table. Because the depreciation will be the difference between the price that we knew for the paid for the new vehicle and the price that we get for it when we sell it second hand. That makes sense? Yeah, so if we sell it after 4 years for £8,000, then the total depreciation in the 4 years was £27,000. Because that's the value it lost over time. And in this case, we're not assuming that we're calculating it using a formula, but when we're taking these numbers, which we know we are estimating from our knowledge of the second-hand market, the sum of money that we can get by selling it on the market. Okay? So this is our depreciation. So that's the total cost. But in fact, we don't want to minimize the total cost. Because what is the total cost going to be? Well, after 1 year, the total cost is going to be £6,000 for running costs and £13,000 for depreciation. So £19,000 altogether. Right? After 2 years, the total cost is going to be, this is 10,500 depreciation and 13,000 running costs. So it's going to be larger. And after 3 years, it's going to be even larger because the vehicle's lost even more value, and we've paid another 8,000 for the running costs. And after 4 years, it's going to be even larger, and so on. So if we were trying to minimize the cost, we would always sell it after 1 year, because the total cost is rising. But we're not really interested in the total cost as such, but we're interested in the total cost averaged per the number of years. So how much it is per year each vehicle. Does that make sense? This is what I will call the average total cost. And this, well, I can say this is the total cost divided by the number of years. Okay, so I'm not using any formulas, which is maybe confusing, but I'll switch to formulas in a second. So now I think we understand the problem. Or maybe we understand the problem even less than before I started explaining it. Okay, let's go on. Okay, so what is the decision going to be that we're making? The decision is what? I just asked it, so you know it, yeah? Yes, after how many years we sell the van, or reformulated, how many years should we keep the van for? Okay. So we'll call this number n. So this is the number of years that we keep the van for. And that's something that is, in terms of OR terminology, this is going to be called the decision variable, or a decision variable. Decision variable in a model like this is a quantity whose value we can choose by our managerial decisions. So this is exactly the decision we want to make. How many years do we keep the van for? That's a decision variable. Okay, and decision variables, there are usually many, but in this example, there's only one decision variable because that's the only decision we want to make in this model. Okay? And decision variables are part of every model that we'll be looking at. So that's an important part. And then another important part of this kind of models is the objective. And so we've talked about the objective. The objective was to minimize the average total cost of the vehicle, consisting of the running cost and the depreciation. So, what do I want to say? Okay, now it's time to use mathematical letters for the quantities that we are given. So let's say that P0 as price 0 is the purchase price of the van. Pj is going to be the trade-in price of the van after j years, or at age j, you could say. I'll change this to aged. And then the last thing we're given in the table is the running cost in each year. So let's call this CJ, C for cost. We can call it anything we want, but let's all stick to C. So this is the running cost of the van in year J. That's rubbish. Yes?
I just wonder, if you decide to trade in the van at the 30th, would you add up the running costs from the previous?
Oh, yes. And we're just going to do it. Yeah, so of course the running cost over 3 years is the sum of the 3 running costs. Whereas the depreciation is the difference between the trade-in price and the new price. No, the other way around. But okay. All right. So we've just summarized the data that we have. Now, unfortunately, in this technology, I will do something you don't like, and I'll make all this disappear. You'd better get used to it, because that's what I'm going to do every time when I want something to disappear. Okay. So now we can start actually calculating things, but we'll be calculating them in a general way using just those letters that I've just introduced rather than those numbers. And then when we get to the final formula, we'll plug in the original numbers that we have. Okay? So let's say that the depreciation after n years is dn, let's say. So how do we get this? I said that a number of times already, so you know that this is the PN, the price that we're selling the vehicle for. No, it's not, is it? It's the P0, that's the price that we paid for the vehicle new, take away the amount of money that we get by selling it on. Okay, so it's the difference between what we paid for the vehicle and what we get paid when we sell it on. That's easy. That's one of our costs. And then what is the running cost for n years? So the total running cost when we keep the vehicle for n years. Let's call it Rn. Yes. So the J can be anything. Yeah. If you put 3 instead of J, you get the third year.
No, it's just because you put N.
Yeah. If you put N instead of J, then you get N years. If you put alpha, then you get alpha years. But that's the brilliance of mathematics. Yeah. You put anything instead of anything as a substitution, and it works. So yeah. So if I want the cost after n years, I have to put n there. If I wanted it after 7 years, I would put 7. Okay? Does that make sense? Does that make sense to everyone? Yes. I used J before, but now I'm using n because n is the decision variable, and what we're interested in really is the cost after n years, because we said n is the number of years that we keep the vehicle for. The running cost can be written as, well, the cost in the first year plus the cost in the second year, and so on, plus the cost in the nth year. Okay. And now that answers your question again, because now the J is going to be 1, 2, and so on until n. Okay? So of course, it shouldn't surprise you that there is a shorter way of writing it using this sigma. And now I'll use the J again. So J goes from 1 to n, Cj. Okay. By now, is everyone familiar with this notation? You sure? Okay. Good. I have to make sure. It's not that, yeah. Sometimes students just look at it and say nothing, and then 2 days later they come and say, "Oh, what was this? What was this sign over there?" Okay. So it's better to ask than. I'm sure someone will come and ask me about this. Okay. So we've got this. Now the total cost where's the book? I'm probably using different letters to the book. Now I realize, but never mind. Okay, so the total cost over n years is let's call it Tn for total. Okay, and that's an easy formula because that consists of depreciation over n years, which we call Dn, plus the running cost over n years, which we call Rn. And then what we're really looking for is the average annual, I'll put annual. Annual means per year. It's a Latin word or something like that. Total cost, that's the thing that we're after. So what letter shall we use for that? A? Okay, let's do A. It depends on n, and the number of years that we keep the vehicle for. What is the formula? Sorry, Tn over n? Yeah. Any other suggestions? No, it is indeed Tn over n because, well, we're keeping it for n years altogether. Oh, the n here should come in brackets. After n years, we've incurred T of n, and so we divide it by n, and that's the average per year. Okay, any questions at this point? No? So this is the cost that we want to minimize, and we'll see very soon how to minimize it, but let's take a 10-minute break now. Right. Any model like this? Any optimization problem like this? There will typically be 3 components. So when you're asked to formulate a model, an optimization model, which this is an example of, you will have 3 components. And they are decision variables, objective, and constraints. There are always these 3 components, and if you don't have these 3 components, then you're doing something wrong. Okay, I keep saying that, and I will be telling you all the time, so that hopefully you remember that when you're constructing an optimization model, you have to have these 3 things. So the first component in this case is only 1 decision variable. What I'm doing is I'm just summarizing the model that we've, okay, so I should probably say. So that's a summary of the model. So we have a decision variable, which in this case is n, and is the number of years after which we, what's this? We replace the vehicle. Okay. The second component is the objective. In an optimization model, the objective is always to either minimize or maximize some quantity. And that quantity that you're minimizing or maximizing is called the objective function. So in this case, we said it was to minimize the average total cost. And we said that the average total cost, there was a formula for it, something divided by n, and that something was, is it still visible? Well, Tn is the depreciation, so the depreciation we had was P0 take away Pn, when you go back into the formula, and the running cost was the sum of all the C's, Cj's, going from 1 to n, okay? That's what we derived. And the third constraint in this model, so what are the constraints in this model? Well, because of the table that we have, for it to make sense, we can only decide to keep the van for 1, 2, 3, 4, and so on, or 8 years. If we've only got data for an integer number of years, and only 1 to 8. So in this case, we want this n to be in the set of the following numbers, 1 to up to 8. Which is the same thing as saying that n has to be between 1 and 8 and an integer number, a whole number. Okay. So now comes the phase of solving the model. Now the problem with this is, well, what is the problem solving this model, do you think? Any problem? I think the main problem is that the depreciation is just given not as a formula, but it's given in a table. Okay. So we can't really do anything very smart. If the depreciation was given by some formula, then we could if this was a formula, and if this was a formula other than just numbers in the table, it was some function of n, like 3,000 times n, then we could expand all this and then use calculus by differentiating it and putting the derivative to 0 and finding the minimum of that function of n. Okay? That's what we could do if these things were formulas. And that's what mathematicians would normally do if these things were formulas. But they're not formulas, really. They're just a list of numbers. And so in this case, there is very little else that we can do then to evaluate an for all the possible 8 values of n. And that's what we're going to do. So I'll say that because the data are given as a list of numbers, or given in a table, more or less the only thing we can do so the only way to find the optimum, find the minimum cost is to evaluate an for all possible values of n. And we'll do that in a spreadsheet. It won't fit. Okay. So now, how do you put all these things into a spreadsheet? I'll take a book that's been given to me, and I'll have a look at what advice I'm given by MMU lecturers. So it says, at this point, you will often find it very hard to decide how to get started. Yeah, so I don't know what to do. It's a true thing. It helps to think about where you want to end up. So, and it gives some advice. Oh, this is page 23 if you're looking for it, but you don't have to look for it. There are some advice here. Like it says that the data and the decision variables should be somewhere near the top left corner of the spreadsheet. Okay, so I'll start drawing a spreadsheet on oh, come on. This thing hates me. Aha, so in the top left corner, what do I want to put there? So, so I probably want the cost new somewhere at the top of the spreadsheet. So this is going to be in a cell like this. I probably want the table of these numbers at the top of the spreadsheet somewhere. So the number of years, or year, whatever. The trade-in price. There's a name missing. Okay, why am I writing it by hand? That's not a rhetorical question. I'm writing it by hand because yeah, why am I writing it? Because I can think better when I write things by hand than if I do things randomly on the computer. So I think, I don't know, maybe I'm just a different generation. But when I want to solve a mathematical problem, even using the computer, I usually just start thinking about what I actually want to solve and drawing some sketches of how I'm going to do it on the computer by hand. And then once I've made up my mind what I actually want from the computer, I actually do it on the computer. Is it better than going straight away on the computer and doing messy things? I think it is, but I'll try to persuade you on your first assignment in coursework. Let's see. Okay, so this is what the spreadsheet is going to look like. I will have this 1 to 8, the table of these numbers, and then the trade-in price, which I know what it is, and then the running cost, which I know what it is. And then, and so like this, I have all my data at the top of the spreadsheet, okay? And now I can start calculating the various costs. Okay, so that's what I'm going to do. Doesn't hurt to repeat the years again. So I can again do 1, 2, and so on. 8. 8. The next row, I can do the depreciation. So this is going to be D1, D2, and so on. Next, I can do the total running cost. So this is going to be, what do we call it? R. R1, R2, and so on. Then I can do the total cost. So that was what we called T1, T2, so on. And then the average total cost. So that was this A1, A2, and so on. And this will be the bottom part of my spreadsheet down here. Okay. And I have a plan, and then I can go to the computer and actually enter the plan. So I've done this. And I'll try to find it. Here it is. I actually got these numbers. I don't want to spend too much time on how these numbers were obtained, but I'll tell you something anyway. You can see the top here. This is just my table of the numbers that I got in the data. There's nothing special about this. What I know is the total running cost. The total running cost, that has to be the sum. For example, here in the third year, it has to be the sum of these three numbers. So I put a formula in there, which somewhere here I should be able to show the formulas. I can't remember how to. I think I've got the formulas here. Anyway, so I put the correct cell formulas that do all the calculations for me. Okay. I've put the depreciation, that's just the difference between the trading cost and the cost of new. This row is just the sum of the previous rows. The annual average cost is just total cost divided by the number of years. Exactly the way we did the maths. And now I'm going to look and find the minimum. And that will be my solution. So from the spreadsheet, the optimal solution is to replace the vehicle after 5 years. Okay, that more or less solves the problem, but I have some points to make about the spreadsheet. Some principles or rules of thumb, if you like. Okay, so the first thing is that just remarks really. Okay, all the data should be visible. Okay, so you shouldn't hide anything in the formulas. If there's a number that enters the computation, it has to be somewhere in a cell sitting by itself. Okay? Not somewhere in the middle of a formula which you can't see. If I click here, I can see the formula. You see the formula? Can't read it, but don't put any numbers there. Okay, is that clear? Because otherwise you'll get lost and you won't be able to find, if there's an error, you won't be able to find the error. It's just it's impossible, believe me. Also, a second thing is that, related to this, that every piece of data, so every value that you get from the data should only appear once. Well, I think in this case there's not much problem with it, but sometimes you have some number that you're using in various parts of the spreadsheet, and the temptation is very strong to repeat that number in everywhere where you're using it in different parts of the spreadsheet. Don't do it. Just use the one that you're using, and the reason for this is that it's easy to change. So if For example, if the price of the new vehicle suddenly went up, I don't have to do anything. Okay, it's really done itself because everything here, all the calculations are in formula, and I don't have the 35,000 anywhere else. Now I see that if it went up to 38, it would be optimal to keep the vehicle for 60. And I can play around with these things. If it went down to 30,000, then the costs just redo themselves, and the minimum finds itself, and it makes itself yellow, and everything is good. Okay, so this is the advantage of doing things in a spreadsheet, is that it's very easy to investigate what happens if the data change a little bit. You can just try it and test it. So if you realize that actually you are able to get 25,000 for it, well, that's not going to change anything. Hold on, what's going to change anything? If you realize that in year 5, you're actually paying 11,000 rather than 10,000, then things recalculate themselves and you find a new minimum without any effort, really. So that's quite nice. You come up. Which brings me to the third point. I've actually said it, which is that make the spreadsheet make all calculations using formulas in the spreadsheet. I think I've made a good argument for that by showing you that everything just recomputes itself when I change the data a little bit, and I've got the answer immediately rather than having to do something. And you know yourselves that many of you in the labs last week just took out their calculator or did some computations on paper rather than making Excel do everything else. So make Excel work for you is the point. And what else did I want to say? I don't know. Yeah, probably don't want to say anything about the spreadsheet anymore. However, I do want to say something. Yes, I do want to say something. So what I want to say next is that with every model that you make and apply, you should be aware of the assumptions that you're making. What is an assumption? Assumption is something you consider to be true, but there's no evidence. Well, no, that's not a good definition. What is an assumption?
Considering facts that haven't been stated to be.
Yeah, that's probably a good definition. So some statements which I don't know for a fact, but which help me actually do the calculation. Okay, being aware of the assumptions you're making when making the model or when building the model is quite important for the practical implementation of your results. Because if these assumptions are then not satisfied in practice, then the model, the optimal solution in the model, and we talked about this last week, may not be the best solution in the practical situation. Okay? So with every model, always think of the assumptions. And what are the assumptions here? So there's a list of assumptions in the book I just want to mention. So for example, one of the assumptions that we're making here is that the vehicle we're buying is new. Now, we never considered the possibility of actually going to the second-hand market and getting a used one. Oh, that's 2 years old. Maybe that would bring our costs down. We don't know. But the assumption we made in the model was that we're buying a new vehicle. Okay, that's one of the assumptions here. I'll try to save some space. So, and there's the 8 years assumption. I'll just write 8 years. Okay, but you know what I mean. The assumption is that we don't keep the van longer than 8 years because we didn't have the data on the table. So we just assumed that after 8 years, at the latest, we're going to sell the van. And that's it. We also made the assumption that there is no well, I'll call it a technological reason for replacing the van. So we're making the assumption that we're making the decision about when to replace the vehicle solely and only based on the costs. But perhaps in 5 years' time, the vans that, or in 3 years' time, the vans that we can buy are going to be much better than the vans we're buying today. And then maybe it makes sense to replace them earlier than we actually thought we replaced them. So these are the assumptions, and there are probably more. I think it's somewhere in the book. What is it? Page 26. Okay, page 26. You'll read it. You can read the book. It's actually quite good. Are there any questions now? Yes.
That assumption statement is that, say if there was an accident with the vehicle, that class an assumption, would that be included in the cost, would that be a repair when the thing would be assumption?
Yes, that is indeed another assumption is that we don't crash the vehicle. Because if we crash it, then yeah, and that completely changes the movie. Yeah, that's correct. Well spotted. Any more questions? Good. No questions is just as good as many questions. However, yeah, I don't want to talk too much. I've lost the homework. Where's the homework? Everyone's going to catch their trains anyway, so I won't talk much longer. You got the homework. Why not? Where did you put it? Oh, it's here. So the homework, which is on the other side of this sheet. Oh, let me put this up. So what am I doing? The homework wants you to do two things. Thing number one is revisit the example that just disappeared, but instead of using the numbers from for the trading costs that are given in the table, use the numbers that are given as the reducing balance method for depreciation that you learned from Philip's lectures. Okay, just as an exercise to see whether you can implement this reducing balance method. But that's not there yet. Just yeah, you basically just change the trading cost as the residual value of the vehicle in the spreadsheet. The spreadsheet you can download from Moodle and have a look at and study and see how it's done. What else? Another two papers that you can look at that are on Moodle, links are on Moodle, are related to this question 2 here. Okay, so you should read. You don't have to read all the details in the papers because there's some math that's probably too hard for you to understand. But just skim through, read the abstract, read the conclusion, read the things that you will understand. It takes some time to get to the paper. So you click on the link and it opens a library window. So you have to log in with your MMU password, and then you click, give me the full text of this paper, and then it shows something else, and then you have to really want the full text, and then it shows something else. Full text, yeah, and then the PDF. Okay, so it's, so yeah, you need patience to get to it. So have a look at those 2 papers that I've linked for you. And what does the question ask? The question asks the difficulties that had to be overcome in the implementation phase. So again, this is kind of this soft, non-mathematical part, but it's important nevertheless to realize what problems they had with creating a brand new timetable for, what's the other one? Police officer rotas. That's your task for next week. In the labs, we'll do another spreadsheet example. And the point of that example is not a very hard task to do, but the point is for you to test how you will be submitting your coursework assignment. So you know that you will have to submit some coursework assignments. Philip has probably told you, I hope he has. And the way you submit them is you create a PDF file or a Word file, if you insist, and a spreadsheet and whatever is required in that particular assignment, and then you go on Moodle and then you submit it on Moodle, and that's the way we get it. So you don't have to print anything, you don't have to bring it anywhere, you just submit the files, upload them. You can do that from home, you can do that from the labs, you can do that wherever you want. And there we mark your solutions, and then you will see in the marking scheme how many marks you got. So the first one we're doing this Friday, we'll do that together somehow in the labs. Well, everybody on their own basically, but then submit. But this one doesn't count. Okay, this is just a test to learn the procedure basically. Okay, it doesn't count toward the final marks. Right. Anything else that you need to know? Any questions? No? Well, if not, then that's everything from me, and I'll see most of you on Thursday or Friday.